No, I'm going to talk to Jasmine.
Hi, everybody.
Appreciated you not. It was good. The way it went well.
Hi, everyone. Hi. We have a nice full house. This is excellent. Welcome, everybody. This is Julia Shates, Ph.D. defense. I'm Claire Pedersen. I was here a really long time, so I know a lot of you. I'm now at the University of Michigan, and I am one of Julia's co-advisors, along with Tristan Lecuyer in the AOS department. So I get to spend a couple minutes to introduce Julia and talk about all of her things she's done here at the University of Wisconsin. So Julia and I started working together in January 2018. She joined the Lecuyer group in fall of 2017. And she came from University of California, Irvine, where she worked with Gudrun Magnusdottir and did a BS in Earth System Science and a BA in Spanish. So when she came here, we started chatting about stuff, and we met weekly that winter of 2018, and you would come with like a new paper every week and a lot of creative ideas, and that's been a theme throughout. Julia was very creative and very excited about ideas, and we'd have these great conversations. And then we got into summer, and Julie kept bringing papers and stuff, and I was like, hey, this is cool, but let's write some Python code. And Julia was like, yeah, definitely. And then each week she'd have more papers, and I was like, okay, so I'm gonna hand you this Python book, and we'll talk in a month. And I just say this because she was kind of nervous about writing code and learning Python, and not only did she learn it that summer and do an excellent job, now I say, because of your creativity, you actively seek out challenges of like how to code and do things, and has found some really creative ways, as you'll see in this presentation. And so I would say you should feel very proud about your coding skills now. But that was our fun kind of introduction to each other. During Julia's tenure here, a lot of you know already, she's done a lot for the department. She's been a part of several service committees, including winning an award for outstanding service for the department. She's also been a teaching assistant for radars, thermo, grading / teaching assistant for radio transfer. And in fact, won an outstanding performance as a teaching assistant for, was it for thermo? Mm-hmm. For thermo class. Also, just to keep, because we get to talk about all your accolades, so her research has been funded by a NASA fellowship for the future investigators in NASA Earth and Space Science Technology for the last couple years, and before that she's been on projects with me, Mark Cooley, and Tristan Lecuyer. And finally, just recently won an award for first prize for outstanding presentation for the International Precip Conference, so no pressure here to recreate that. So I'll also say in terms of research, Julia has 2 first author publications out. She's working on her 3rd that we're getting out the door this next month. And then also she's very collaborative. She's been a co-author on 3 different papers and worked on several different projects in the field, as well as organizing conferences and being part of big workshops. Finally, I'll say that Julia's next project will be going on to JPL to work with some colleagues there, looking at all kinds of issues related to satellite blind zone, precipitation, particle size distribution, and back to where you grew up in the Los Angeles area. So that's exciting for you and for JPL. And finally, the last thing I'll say, and this is totally sappy, but it's one of these things that happens that you hear about, and then it's fun when you get to experience it. It's so fun to be a mentor and have worked with a student as being their mentor, and then it slowly creeps up on you, and all of a sudden they're your colleague, and they're the ones suggesting the ideas and the direction, and that feeling is really awesome. So thank you, Julia, for all your hard work, and we're excited to all hear about your talk. Thank you.
I am remembering to.
Rena's
there we go. Okay. Cool. Thank you so much for that introduction. Trying not to get emotional now before my talk. Okay. Today I'll be talking to you all about ground-based radar perspectives on the satellite radar blind zone. And firstly, a little bit of background. So our planet is warming, and in the high latitudes, they're warming faster than in other parts of the world, and this results in a lot of changes with precipitation. So we have increasing precipitation in many parts of the world, but also some parts of the world are experiencing a shift from snowfall to rainfall instead. And this has implications for energy balance. So in this figure here, you see this changing snow cover, and that has a lot of implications for albedo of the surface, and then also glacier mass balance, snowpack and water resources, rain on snow events, as well as impacting subsistence hunting, and so people that depend on the snowpack for their way of life. And so we have nearly global observations of clouds and precipitation from our satellite radar observations. But measurements below 700 meters to 2 kilometers above the surface can be unreliable because of ground clutter. Essentially, a satellite radar can detect the precipitation in the cloud, but also the surface can contaminate those measurements. And so this cartoon here is illustrating the concept of the satellite radar blind zone. So on this left panel, we have this snowing cloud that's being observed by a satellite radar, and then this other little cloud, and we can't really see what's going on in the surface. But on the right panel of this cartoon, we have the perspective of a ground-based profiling radar, where we see this snowing cloud is actually raining at the surface, and this other little cloud is snowing over complex terrain. And so having this ground-based radar, this satellite radar blind zone, leaves us with some questions of what is the precipitation phase at the surface? Is there precipitation at the surface? And does that precipitation rate change with height? So ground-based observations provide us with insights for some of these near-surface precipitation processes. And so here are some examples from actual satellite radars. So on the top panel, we have observations from the CloudSat Cloud Profiling Radar, and on the bottom plot, we have observations from the Global Precipitation Measurement Dual Frequency Precipitation Radar, so the GPM-DPR. And so let me get you oriented with these plots, where for CloudSat, we have height on the y-axis, and then lat lons on the x, and this is a snowfall event, and this dark purple near the surface is this area that's contaminated by ground clutter. And then looking at this bottom plot, this is for the same snowfall event from the DPR KU band radar. And so we still have height on the y-axis and lat lon on the x, and we can see that this dark purple near the surface is even larger. So we can see that this satellite radar blind zone is impacting how much we can detect what's going on near the surface. And so this motivates some of the questions and science objectives that I looked at as part of my finance proposal. And so to get you oriented with some of those science objectives that will lead into and be tied into this whole talk is I'm interested in characterizing precipitation regimes and linking those clouds to the meteorological conditions, then quantifying precipitation phase and the height of the melting level, and then assessing the vertical structure of snowfall and relationships to the surface, with an extra focus on this third science objective. So we'll have some key highlights from the first two, but most of the talk will be on the third. But all of these science objectives kind of fit into this more broad question of how can we use ground-based radar observations with ancillary measurements to understand and characterize precipitation variability near the surface. So this is our big question of the entire talk, which we'll tie in and return to and revisit. So a little bit more context before we get into the actual context of the different science objectives. So my framework of looking at precipitation near the surface and using ground-based radar observations is using the profiles of radar reflectivity and Doppler velocity to assess the vertical structure. And so one example of how I do that is looking at the cloud top heights and to organize and separate the different types of regimes. And so this has been done in different ways. So this is an example from Cooley et al. 2016 using CloudSat observations. And so on this top plot, we have an example of a shallow cumuliform snowfall event. And we can see that the cloud echoes are generally below 4 kilometers above ground level. And it's also characterized by a convective snowfall pattern. So we can see pulsing in space in the reflectivity signature. And then on this bottom plot, we have an example of deep nimbostratus snowfall. So this is, we can see the cloud echoes exceed 8 kilometers above ground level. We have a really different pattern in the reflectivity structure in time and space. And so this is one example using CloudSat observations. This can also be done using ground-based radar observations. And so this is an example from Pedersen et al. Looking at ground-based observations from the microrain radar, which is a vertically profiling radar in the upper Great Lakes region, so Marquette, Michigan. And so now on the y-axis we still have height, but on the x-axis now we have time. So on this left plot we have deep synoptic snowfall, where we have our precipitation echoes reaching up to 3 kilometers above ground level. And on this right plot, we have shallow lake effect snowfall. So the precipitation echoes are below 2 kilometers above ground level. And it also has this characteristic convective snowfall, where we see pulsing in the reflectivity with time. This has also been done in observations from the Ice Pop campaign. And so here we have an example of an event that transitions from deep snowfall to shallow snowfall to then even closer to the surface, where we see that the cloud echoes are defined as near surface. So these are very shallow echoes. So having this satellite, tying back to the satellite radar blind zone, because we have this area that's difficult to detect precipitation near the surface, it leads to underestimates and under-observation of shallow snowfall. And this has been shown by a number of studies. In addition, scanning radars, so weather radars, also have this effect where it's difficult to detect shallow precipitation the further away you get from the radar. And this has actually been shown using satellite observations, which is kind of a fun way to tie them in together. And so it actually matters what kind of snowfall regime we're looking at and how often they occur, because they have implications for accumulation and albedo. So this is an example from Cooley et al. 2016. We're on the top, so for both of these plots, we have percentage of annual estimated snowfall accumulation. And on the top plot, we're looking at shallow cumuliform snowfall, and on the bottom plot, we have the deep nimbostratus snowfall. We see at different parts of the world have different occurrence frequency of accumulation for these different regimes. Then, McElhatton et al. 2020 looked at different regimes based on cloud phase, so fully ice regime where the clouds are generally deeper, and then a mixed phase regime, which is generally more shallow. And they looked at the snowfall mass contribution to the Greenland ice sheet. And so different seasons have different occurrence and accumulation from these regimes, which has implications for the albedo of the Greenland ice sheet. So that connects the implications for accumulation and also the albedo of the surface. So in addition to snowfall, the vertical structure of precipitation and the radar reflectivity and the Doppler velocity can be used to identify the signatures of melting or change of phase in the radar. So here's an example from White et al. We have height on the y-axis, and one of these curves is Doppler velocity, and the other is a signal-to-noise ratio. And it's essentially showing that you can use these different characteristics and changes in height to identify where is there melting happening. And this can be done with a number of different radar variables. And so one really nice example I like is from Canada et al. 2017, looking at the bright band height. So the bright band is the height where we see that melting happening in the radar. So this is using GPM, DPR, so that's satellite radar bright band heights. And the color is telling us how close it is to the surface. So what we're seeing is that some of these, the lighter blue colors are closer to the surface, and the more orangey red colors are melting happening higher above the surface. And we can see at higher latitudes, we have melting closer to the surface. So this has implications for high latitude detection of melting. And also, if we think about melting over more complex terrain or over land surfaces, which are more difficult, we have a higher blind zone there, then this kind of hints at some of these challenges for detecting those phase transitions. So in addition, it's been shown that the height where melting is happening, so that melt level in the atmosphere, there's a trend of increasing melt levels, which has implications for are we getting rainfall or snowfall at the surface, making it even more important to identify what kind of phase are we getting. And so many are probably familiar with using a simple temperature threshold in order to separate between rain and snow, but actually this is not always the most straightforward. So this is a nice plot from Jennings et al. 2018 compiling surface station data for the Northern Hemisphere. And it's showing the 50% rain-snow temperature threshold. And so all these different circles of colors, these oranges and yellows, are really telling us that surface temperature for 50% rain or snow varies regionally. So different parts of the world, we're seeing higher temperatures occurring with snowfall. And so this has implications for a priori assumptions for a satellite retrieval of precipitation. So are we going to use a drop size distribution or a particle size distribution for a retrieval? And knowing that in advance is important. And also makes it important to understand how can we use the radar observations to detect phase. So the way I do this, the way I explore these topics of vertical structure, snowfall, and rainfall is using ground-based remote sensing instrument suites. So in this map, I'm showing the sites from which I use observations. So I use observations from the North Slope of Alaska, Marquette, Michigan, and the Upper Great Lakes region, and then Halkalusetta, Norway, and Kiruna, Sweden. And so at the Upper Great Lakes site and in Scandinavia, we use observations from a micro-rain radar, which is a K-band vertically profiling Doppler radar that detects precipitation falling towards it. In the North Slope of Alaska, I use observations from a Ka-band arm zenith radar, which observes precipitations and clouds. It's a 35 gigahertz vertically profiling radar. And at the two sites where I use the MRR, the micro-rain radar, I also use the precipitation imaging package. And the PIP is a custom NASA distrometer that allows us to detect the microphysical characteristics of hydrometeors at the surface. In addition to those observations, I use surface meteorological ops as well as reanalysis from ERA 5 and MERA 2. And I just want to point out that this image here is from Marquette, Michigan, a day where it was snowing. And what we can see, so this is the National Weather Service office, so here's the micro-rain radar shown there. The PIP is kind of in the corner, I'll show some pictures soon. And then here we see the next rad radar as well. So here's an example of videos from the PIP. So this is the instrument where we get our microphysical characteristics of the hydrometers at the surface. On the left we have the rainfall, and on the right we have snowfall. And so from processing these videos, we obtain the drop size distributions, the particle size distributions for snowfall, the fall speeds of the hydrometeors, and then we can obtain the effective density and also the snow liquid water equivalent rate and the rain liquid water equivalent rate. So for this work, there are multiple parts because there's multiple years, multiple instruments. And so I promised we'd return to this question of how do we use these ground-based radar observations to characterize the precipitation variability. And so we have a few parts here. The first one will be highlights on snowfall regimes, and that's looking at observations in Scandinavia. The second part is looking at phase discrimination, and that's in the upper Great Lakes region. And then the third part, which we'll spend the most time on, is the vertical structure of snowfall regimes and satellite detectability, and that's in the North Sobo Classic. And so I'd like to re-emphasize that these first two parts will be key highlights, so they'll be shorter than the third part. So we'll begin with this first part, looking at snowfall regimes. So for this work, we looked at high latitude precipitation, snowfall regimes at 2 distinct sites in Scandinavia. And so I used observations from the high latitude measurement of snowfall field campaign, where we had instruments deployed in Haukeliset, Norway one winter, and then the following winter in Kiruna, Sweden. And the questions we asked is, how are snowfall regimes similar and different at these varying regions in the high latitudes? So Haukeliset, Norway is this mountainous region and complex terrain, and Kiruna, Sweden is in a much colder, drier region, and it's not in an area of complex terrain. Then we asked, how is the macro and microphysical character of snowfall influenced by the local environment versus the larger scale synoptic weather patterns? And so here are examples of the snowfall regimes defined by the radar observations. So I used the precipitation echo top heights in order to separate the different regimes, and I'm showing you examples here. So on the top plots we have observations from the radar, so the vertically profiling MRR, and on the bottom plot we have the PIP observations. I'll walk through them. So the shallow example we can see, so it's height on the y-axis, hours on the x, and then the color is radar reflectivity. So in the shallow we can see the precipitation echoes are below 1 kilometer above ground level. So this is an example that would be fairly difficult to detect using a satellite radar. Then the deep snowfall is in this middle plot, so we can see that the precipitation echoes reach the operating range height of the radar, which is 3 kilometers above ground level. Then the intermittent snowfall regime is characterized by its both height above ground level, so it must be above 2 kilometers above ground level, and also has pulsing and reflectivity with time, so we can see enhancements in reflectivity as the hours go. So then on the bottom plot, we have the corresponding PIP observations for these 3 example events. So the color now is the particle size distribution, and the y-axis now is the particle diameter. And so we can see for the shallow, so we have relatively fewer particles than in the deep and intermittent snowfall, but some of them are larger. Then for the deep snowfall, we see this really bright yellow for lower diameters, and that tells us there's a lot of small snowflakes, especially compared to the shallow and the intermittent regime. And then for the intermittent, we're seeing that enhanced yellow area, so lots of small particles, but also we can see that the microphysical characteristics at the surface match up with what we see going on in the radar. We see this pulsing and reflectivity, and we see a pulsing in particle size. We see larger sizes that line up with that enhanced reflectivity. So just using these definitions of the precipitation echo top heights and how it changes in time to identify and categorize different events for these two different winters, we combined these cases to compare how they are in a more composite sense. And so for this next plot, I'm showing observations from the ERA 5 vertical profiles of temperature and relative humidity. And just to get everyone oriented, on the 2 plots on the left, we have observations or reanalysis from Haukeliset, and on the right, we have Kiruna. And we're going to spend our time right now with the relative humidity. So on the y-axis, we have pressure, and on the x, we have relative humidity. and each color is for one of the regimes. And so what I'd like to do is draw your attention to the blue curve, which is for deep snowfall, and we see that's high relative humidity throughout the free troposphere for this deeper snowfall event. For intermittent snowfall, we see that the relative humidity is higher close to the surface, but it's more variable aloft. And then for shallow snowfall, the free troposphere is dry, but then the relative humidity near the surface is moist. So we can see that even for these two different sites, we have similar types of vertical profiles of temperature and relative humidity. So in that short little section of key highlights from part 1, I showed that there's common snowfall regimes observed at these distinct locations, even though they have different geographic characteristics, and that they share similar moisture and temperature profiles. And so this could be important for assessing those difficult to detect shallow snowfall regimes, especially the fact that we have higher moisture near the surface. So let's transition to rain in the upper Great Lakes region. So this again will be some key highlights from this chapter. So for this rain, we're interested in stratiform or cold rainfall. And so here's a cross-section of a stratiform rain cloud where we have height on the y-axis. And so we have snowfall forming aloft by vapor deposition. The snowflakes aggregate, encounter a melt level as they fall, and then reach the surface as rain. And this height where it transitions from snow to rain is what I'm referring to as a rain-snow level. And so I did a multi-year analysis of rain-snow levels at Marquette, Michigan. And here's another picture of the instruments at Marquette. So the PIP is on the left with this bright light camera, and bright light in the camera, and then the MRR is over there on the right. And so we looked at about 6 years of observations from the PIP and the MRR, and we asked the question of how do the rain snow levels vary throughout the years? What differences do we see in the macro and microphysical characteristics of rainfall as a function of those rain snow levels? And then how can these observations be coupled with ancillary measurements to better address uncertainties and retrievals of surface precipitation type? So a brief description of the rain snow level identification. So here's some MRR observations. On the top we have radar reflectivity, and this is a rain to snow event. On the bottom plot we have the Doppler velocity, which is a measure of how quickly the air is falling towards the radar. So how quickly are all those snowflakes, all this rain falling towards the radar? And so what we can see in the radar reflectivity is a really distinct line of darker reflectivity, and that's the bright band. And in the Doppler velocity, this transition from snow to rain is even larger, it's even more noticeable. And so we can see as everything is falling towards the radar, in these positive colors, and the sort of light reds, then we have this dark red blob. And that dark red blob is rain. And that stark difference between the snow aloft and then the rain below is how we detect the rain snow level. And so developed a method to identify that and applied it to all these years of observations. So here's that superimposed rain snow level that identifies where it's raining, but then later in the event, we're not incorrectly flagging any snowfall. So I applied that to all these years of data and got a distribution of the rain snow levels for each month. So here's box and whisker plots. So on the y-axis we have height above ground level, and each one of these boxes is a month. And then we have a 1/2 violin plot that shows the empirical distribution of the rain snow levels. And so just from this one plot, we can answer a lot of questions. So we can see that there are higher rain snow levels in the summer. We can see that they're lower in the winter months, and that in the fall and the spring, it's pretty variable. So if we were to point out May and October, we can have a rain snow level closer to the surface at 1/2 kilometer above the surface, but also we can observe a rain snow level closer to the operating range height of the radar of 3 kilometers from ground level. And so this directly has implications for that satellite radar blind zone. So if we're going to be able to detect that signature of melting within this range of 700 meters to 2 kilometers above the surface. And so this is kind of this area of difficult to detect rainfall transitions. So next, we wanted to compare the microphysical characteristics of the rainfall near the surface. So in order to do that, as a function of rain snow level, we separate the different rain snow levels into height categories. These are our 4 height categories. So now I'm showing observations from the PIP. So on the y-axis, we have the drop size distribution. So these are mean drop size distributions for each of the height categories. And on the x-axis, we have the equivalent drop diameter. So what we can see right away, or it may be difficult to see from over there, but the arrows are pointing them out, that rain snow levels above 1.8 kilometers above ground level, we see a higher number of small drops. And then for rain snow levels below 1.8 kilometers above ground level, we have a higher number of larger hydrometeors. So let's take a look at the mean fall speeds. So now this plot is showing fall speed on the y-axis, the drop diameter is still the x, and what stands out is that for lower rain snow levels, we have lower fall speeds for the same equivalent drop diameter. And so what this could be suggesting, combined with the fact we have a higher number of larger hydrometeors, is that when the rain snow level is closer to the surface, we could also be observing some mixed precipitation or melty snowflakes. So then we're looking at, in this next plot, the rain rates from the PIP. So we have on the y-axis the counts, and the x we have rain rates. And in the yellow and green rain snow levels, which are higher rain snow levels, we see higher rain rates. So combined with these microphysical characteristics and the rain rates and the radar observations, or the reflectivity observations near the surface, which I don't have enough time to show you everything, this has implications for retrievals of rainfall. So we also looked at ZR correlations and found differences for the different rain snow levels. So then we wanted to compare the radar to reanalysis. And so reanalysis products are used directly in satellite retrievals, so it's important to assess and explore how the reanalysis compare to ground-based radar observations. So what I'm showing here is a scatter plot comparing the MRR rain snow levels to melt levels derived from reanalysis. And so those melt levels are wet bulb temperature isotherms. And so this first plot, the melt level is defined at the wet bulb isotherm of 0 degrees Celsius. And so what this is showing is that all the reanalysis melt levels are generally below the MRR rain snow levels. And so that makes sense because as you have snowflakes falling, encountering a layer of wet bulb temperature of 0 degrees Celsius, they begin to melt, but the radar is not going to detect that right away. So it takes some time and some distance for that to be detected. Next, we looked at a slightly warmer temperature of 0.5 degrees Celsius and saw that there was a slight shift and more agreement between the MRR and the reanalysis. And finally, we compared the 1 degree Celsius wet bulb temperature isotherm and found really good agreement between the MRR rain snow level and the reanalysis melt level, particularly at this temperature. So those were some key highlights from this part where we show the rain snow levels vary seasonally and influence the microphysical characteristics of rain at the surface, which has the implications for both retrievals and also detection in the satellite radar planes. And then we compared the reanalysis derived melt levels to the MRR rain snow levels and found generally good agreement, which gives us lots of confidence in reanalysis products with that. And then finally, we're going to shift to this third part, which we're going to spend most of the time of the rest of the talk on. And so these two, first two parts kind of build up to some of the background and knowledge and understanding to address some of the methods and questions that we have in this final part. So in order to assess the vertical structure of snowfall and satellite detectability, I use observations from the North Slope of Alaska DOE ARMS site that's located in Utqiagvik, Alaska. And so here's a picture of the radar installed in Utqiagvik. And this site is pretty high latitude. It's a cold region where the sea ice is frozen for many parts of the year. It's coastal and it's low elevation, so it's about 3 meters above ground, 3 meters elevation. So here I'm showing examples of the 5 snowfall regimes now that I'm looking at for this part. And these are 5 snowfall events that were detected, and I'll explain the detection method in the next few slides. But first I want to show you the regimes. And so on the top plot, we have single layer snowfall regimes, and I'm using definitions from cloud top heights from Jean et al. 2020. So in the deep snowfall here on the left, we have the cloud hechos are defined as being above 4 kilometers of ground level. And then we have a shallow example where we see the definition of the shallow regime is cloud tops between 4 and 1.5. And then we have an example of near surface snowfall regime. So I'd like to point out that that y-axis is different than the other y-axis because it's so close to the surface. So this would be an example of a very difficult to detect snowfall event where the cloud echoes are below, they're even below half a kilometer above ground level. Then we have an example of the other 2 regimes used in this study. So we have snow virga here on the left where we see the cloud bottom boundary does not reach the surface. And then we have an example of multi-layer snowfall, which is defined as having more than 1 layer. So it's a detached layer of 2 separate layers of cloud and snowfall occurring. So in order to get to these events, there's a few steps. So first we have cloud precipitation boundary detection. So just to get you reoriented, we have height on the y-axis, time on the x, and this is a deep snowfall event. identify the boundaries, and then use just the boundaries in order to separate and classify them. So using those, I showed them just in the slide before, but here's my definitions for the different regimes. So there's a few more steps to separate between cloud and snow and rain. And those steps include a reflectivity threshold near the surface. So the reflectivity must be above -15 dBz. The Doppler velocity near the surface must be less than 3 meters per second. And there must not be a rain snow level detected. So this is where I take what I used from Marquette to then apply it to different radar and essentially exclude rainfall events instead of grab rainfall events. In addition, we use a wet bulb temperature threshold near the surface where all the events must be below 0 degrees Celsius. Then each event must consist of at least 25 minutes and must be at least an hour away from another event. In order to assess satellite detectability, we compare Kaiser to what I'm calling cloud-set bin Kaiser, which I'll explain next. So what we do is we look at Kaiser, but then in cloud-set bins. So the Kaiser has a high resolution, or high range resolution of 30 meters, but in order to compare to cloud-set, we use 240 meter effective bins. So we take means of these bins. Then the lowest usable bin in Kaiser, this is our surface level, is 160 meters above ground level. But for Kaiser and cloud-set bins, we're using 850 meters above ground level as our bottom surface bin. Then we apply a 5-minute running mean, and that's to simulate a cloud-set footprint. So essentially we take Kaiser and we chunkify it. So here is my two sisters' cats representing Kaiser here on the left, and cloud-set bin Kaiser, aka Chankazar. So they'll be joining us for the remainder of the slides. So here's an example of Kaiser observations on the left. We have kind of a complex case where we have where we have snow virga starting at the event, and then that transitions into a shallow snowfall event. But in Kaiser, we can see we lose some of that definition and the resolution. In addition, we see that in some areas where there's snow virga, we're actually not able to tell if it's sublimating near the surface or not. In some areas where we have higher reflectivity close to the surface, those are also not detected. They're smeared out and also below the blind zone. Here's another example of an event. So we have Kaiser on the left, and so this is a very shallow snowfall event where we see reflectivities though reaching 10 dBz in some spots. So we have some nice snowfall in there, but in Chankazar, or in cloud-set bin Kaiser, we're not seeing anything. So this would be an example of it's completely undetected because it's within this blind zone. So we take that method and apply it to all of the snowfall events for all the single layer regimes and compare the snow and cloud top height distributions. And so the black curves are for Kaiser, the green curves are cloud-set bin Kaiser, or Chankazar. And what we have on here is the height on the y-axis, and all the x-axes are counts. So we have 1D histograms that are transposed, they're flipped. And what they show us is, what I'd like to really point out in particular, is these months that have high counts of near-surface snowfall, near-surface snow and cloud tops that are undetected in Chankazar. So basically, when you see these black curves, but then there isn't a green curve that follows. So these are cases where just the snow and cloud top heights are too shallow. We could not detect that in a cloud-sat radar. So then we take all of these snowfall events and we composite them in a 2D histogram. So this is the vertical structures of the regimes. And so what I'm showing is we have the height on the y-axis, reflectivity on all the x, and then the color is the count. So it'll tell us how many counts are there of a reflectivity at a specific height bin. So on the top plots we have Kaiser, on the bottom plots we have Chankazar. And so we can see some things that are consistent between the two regimes. So with deep snowfall, we see this increasing reflectivity towards the surface. In shallow snowfall, we see some of that as well. But then in the near surface snowfall regime, we're really seeing that impact of the satellite radar blind zone. So there is a high concentration of near surface snowfall counts in the reflectivities that are not detected at all in Chankazar. And that's a really high concentration of points. Then we relate reflectivity at our surface bin height for Chankazar and our surface bin height for Kaiser. So on the y-axis, we have our Chankazar heights. That's at that 850 meters above ground level of reflectivity. And on the x-axis, we have the surface height reflectivity from the Kaiser. And so this is also a 2D histogram where the color tells us the counts. So starting with deep snowfall, we also have a 1-to-1 white dotted line. So for deep snowfall, we see that the reflectivities near the surface are generally between 0 and 10 dBz. And also that there's pretty good agreement between 850 meters above ground level and 160 meters above ground level. So that has good implications for retrieving snowfall of this type of event from a satellite radar. Then looking at shallow snowfall, we see a shift towards lower reflectivities observed. So most of the reflectivities are between -15 and probably 5 dBz. And however now, there is a small shift, it might be hard to see, of the reflectivities observed at 850 meters above ground level are slightly lower than what's being observed at 160. And so this would suggest that if you're retrieving the snowfall at a higher level than the surface, that you could be getting a small underestimate in the snowfall amount. Then for the near surface snowfall, we're seeing the least agreement between the two different levels. And what we can see also is there's a shift towards lower reflectivities. And this high concentration of points of the reflectivities is most of the observations are around -15 dBz, -15 to -5, but at 850 meters above ground level, it's even lower. So this would suggest if you're just getting that reflectivity at the top of this little near surface snowing cloud, that is going to lead to an underestimate of the snowfall amount. So in addition, we looked at the vertical structure of snowfall regimes for the multi-layer and then the snow virga. So we have multi-layer on the left, snow virga on the right, and Kaiser on the top, chunks are on the bottom. And for the multi-layer, we're not seeing like a distinct layer here because we have a lot of variation in the types of events. You can have different geometric thicknesses, different distances between that second layer. So we don't really see a super well-defined upper layer, but this lower layer, we have a lot of reflectivities near the surface. Then for snow virga, most of the observations are above 3 kilometers above ground level, and then we see kind of tapering off. But some of the observations could be flagged as snowfall at that 1 kilometer above ground level. So for some of these, we may not be able to separate out that that's actually sublimating before it reaches the surface. And then for that multi-layer snowfall, there's a high number of counts that are not observed in Chankazar. So let's populate this table together. So firstly, we have the regimes on this left column, and then the occurrence, and this is for May 2011 through December 2021. And so what really stands out is that the near surface snowfall has the highest occurrence of all 5 regimes. So 32% of the snowfall detected in this time period is near surface snowfall, followed next by shallow snowfall, snow virga, deep snowfall, and then the multi-layer snowfall. So for this last column, we're going to populate this column together and work through some different definitions as well. So this column is about the misidentifications in Chankazar, and the CloudSat bin to Kaiser. So what could we be detecting using that CloudSat radar? So first, are those observations underestimated? So when I mean underestimated, I mean that the reflectivity at 850 meters above ground level is less than -15 dBz. And so we can see that for all these regimes, there is some underestimate in the reflectivity at using a higher level than the surface. And this is particularly notable in the multi-layer snowfall. Next, here's the undetected information. So that would mean that there is absolutely no reflectivity observed in Chankazar at 850 meters above ground level when the Kaiser observed snowfall at -15 dBz. And so what really stands out here is that near surface snowfall regime, which happens 32% of the time in this time period, but 76% of those events would be undetected in Chankazar. And then also in the multi-layer snowfall, that lower level is also difficult to detect. Then for snow virga, 6% of the time we have an incorrect flag. And so that would mean that the reflectivity at 850 meters above ground level is above -15 dBz, but in the Kaiser, we're seeing no observation of snowfall at the surface. And so this happens 6% of the time for the whole time, but it varies for different months, which I don't have time to show everyone today. But it can go up to 9% for some of the cold season months. So it can be important there. So for those who would like to see that visually, I just wanted to bring back these examples from before, what I mean by incorrect flag, underestimated, and undetected. So here's that snow virga to shallow snowfall event. So where the snow virga is, where we're not detecting that it's snow virga, that would be an incorrect flag. And this later part would be an underestimate because we're seeing higher reflectivities that are just not detected. Then here's that undetected snowfall event. So to put that into context again of that table. So finally, we took our ground-based observations, and we bridged the link to the satellite radar observations. And so what I did is I used CloudSat cloud profiling radar observations for overpasses that were within 100 kilometers of Kaiser in Utqiagvik. And I only used the preset flags that are snow certain and snow possible for surface types land and ice. And also, these overpasses have to match up with regime snowfall events. And so here's our site, Utqiagvik, with that 100-kilometer ring around it and a little cloud set right there as well. So here are the results from compositing these events. And so we have, here's our cloud set here, and then from left to right, deep, shallow, near surface, multi-layer, and snow virga. And so again, these are Kaiser CloudSat matched events that have snow flags. So this is not all the possible overpasses of CloudSat reaching around Utqiagvik, just to re-emphasize that. So some of the things we can see that we would expect and hope to see is the steep snowfall. We see higher cloud echoes, increasing reflectivity towards the surface. The shallow snowfall, we have this high concentration of points, especially within 3 kilometers above ground level, which fits perfectly in our definition of shallow snowfall. For near-surface snowfall, we don't have a lot of reflectivities in this 2D histogram, which goes with what we would expect. And then for the multi-layer snowfall, we actually do see an increasing, this high concentration of reflectivities below 2 kilometers, in addition to some of these sort of messier 2D histogram characteristics of lots of different multi-layers on top of that in there. And then for our snow virga, this is not all CloudSat virga. So you can separately look at virga in CloudSat, but that's not what we're doing here. We're comparing the Kaiser snow virga to snow flags in CloudSat. So what we do see is a high concentration or an increase in concentration of points around 2 kilometers above ground level. And then we do see a slight curve of decreasing reflectivity towards the surface, which could be indicative of that snow virga. So then this is a qualitative comparison to Chankazar. And so keep in mind that when taking these different events, there's spatial heterogeneity of snowfall. So across space and time, the events aren't going to match up perfectly. But qualitatively, this is an interesting thing to look at. So remember, this is all of the Kaiser events, and those are just the Kaiser CloudSat matched events on the top. And so we do see a pretty good agreement between deep and shallow snowfall. Not a lot going on with near surface, which is what we would expect to see. And then actually multi-layer showing up nicely. And then we would not expect snow virga to match up with the virga and Kaiser. That would not be the match up there, but still a qualitative comparison. So from this part, what I've shown you is that the results show monthly differences in the snowing cloud topic distributions. And there's variations of the vertical structure for the different snowfall regimes. And really, what I'd like to highlight is that these results show challenges in detecting reflectivities near the surface. So when we're seeing those near-surface reflectivities, or when we shouldn't be detecting anything near the surface in the case of snow virga. So essentially what I've done to answer this question of how we can use ground-based observations with these ancillary measurements is I've leveraged ground-based remote sensing instrument suites to characterize snowfall regimes at 2 different sites using different types of radars, explore microphysical processes near the surface. We looked at drop size distributions today. And then quantify precipitation occurrence in the satellite radar blind zone and what that would mean for retrievals. So ground-based remote sensing instrument suites like these are also really important for validation. So similar, we looked at the blind zone here, but validating retrievals and then also developing and new retrievals and also improving retrievals that are currently in use. In addition, there are new methods that can be used, such as machine learning, to kind of fill in that gap of the blind zone. So a big part of what I'm interested in and how this work is important is it has implications for future satellite radars. So right now, we're expecting EarthCare to be up soon, and the atmospheric observing system is being planned. So seeing these types of observations is important for assessing radar sensitivities. What do we need in order to observe these types of clouds and snowfall? Also, what variables are useful for retrieving the precipitation? And these new radars up in space will have Doppler radar capabilities. And so how can we use features from ground-based radars of Doppler radar, so that Doppler velocity that I showed you today for phase transitions, how can we use that kind of information to assess future satellite radars and retrieving phase of precipitation and retrieving precipitation itself? So those are my references for today. And I would like to make some acknowledgements, and oh no. Okay, so I wrote stuff down because I knew that could happen. I'd like to acknowledge my advisors Claire Patterson and Tristan Lequier. I'm so lucky to have had you both advising me. You're extraordinary scientists and supportive and encouraging people, and I look forward to continuing to work with you in the future. In addition, I'd like to thank my PhD committee who have had such insightful questions and feedback, and I look forward to talking more with you all as well. I want to thank Pete, whose technical support for the last 6 years has been so helpful in my research, in mentoring, and teaching. Amazing, thank you, Pete. I'd also like to thank many group members at UW-Madison and also at University of Michigan. I'd like to especially by name acknowledge Juliet, Aaron, Norm, Dave, Jan, Fraser, and Jack. Thank you for your feedback and support, taking time to help me, talk with me, and give me feedback. I'd like to acknowledge some members of the original Polar Coffee Group. So that's Anne, Ellen, and Marion. We've been meeting since 2018, and we support each other, and we've been continuing to meet even over Zoom when we're at different places, and continue to look to each other for support. I'd like to acknowledge the AOS department, faculty, and staff. With your support, I feel like I've had so much encouragement in being able to go on a lot of adventures as well. I'd like to acknowledge my friends and family and my husband, who've been so loving and helpful. Thank you so much. And of course, it wouldn't be a science talk if I didn't take time to acknowledge that my research has been funded a lot for NASA Finest. So thanks to NASA. Yeah. So with that, thank you so much. I'm happy to take questions.
Thanks, Julia. I guess since you have two advisors, I'll take the turn at the end of the talk to oversee any questions. Maybe we'll start with Hamish. Start with early career scientists if possible, and then we'll move to more senior people after. But Hamish.
Really nice talk. Thanks so much. I'm really intrigued by your near-surface snowfall. I'm wondering how much of that could be blowing snow, and if you had a way of accounting for that, and if there was overestimation of snowfall based on blowing snow.
Right. So I have not included any thresholds to separate out blowing snow, and I've talked to a few people about using a wind threshold. And I know that the blowing snow problem is particularly important in Antarctica and some other places. It definitely happens here as well, and so that could be a next step. It's a good question.
Another question? Yes, go ahead.
For your second part, when you were showing the DSD evolutions based on the different rain snow levels, I'm wondering, have you considered looking at the MRR's spectrum width to see if those evolutions are forming due to where that rain snow level is? Is it forming due to differences in the spectrum above that melting level? And trying to understand where that's coming from, if it's just, evolution.
So I have looked at spectrum width in terms of like, should I be using spectral width to identify versus Doppler velocity, and I stayed with Doppler velocity, although that's another variable that can be used. So those drop size distributions are at the surface, and so it's, if there are changes in the spectral width above the melt layer or something, that's not exactly, that's not like a direct matchup of that DSD is for what's going on above, but that could be an interesting thing to see. How does the spectral width develop differently? Do we see differences? Anything kind of like turbulent going on above the melt layer would be really interesting to see. I haven't done that yet, but that's definitely another variable that is explored for these topics.
Thank you.
Yes, all the way back.
What it me was, nice job, very cool stuff. So your last result there, you did the qualitative comparison between the Champ-Car, how do you say that, and the physical Cosset itself. Have you thought about actually matching the events that you have available from Cosset to do a more close comparison?
Right, that's a great question, and as I was putting the slides together, I'm like, that's a perfect next step, and so I'm glad you asked that, because it's just literally a back match of like, okay, we have these events that we matched, now we'll just match them back and then make these 2D histograms. And so I think that's a natural next step for sure, of like what figure would be like the next smooth one to look at. So thank you for bringing that up. It's definitely like a next step idea.
Go ahead with Brad first and then Grant.
So for your Marquette study, as I understood it, particularly in the wintertime, you were only looking at events where there was a melt layer, right?
Yes, yep.
I would assume they're probably a small fraction of the actual precipitation events at that time.
Right, so there's particular years that have more rainfall in the wintertime than others. Claire would remember the exact year. I think it's 2018, you said?
2019.
2019, okay. There was a year with a lot of freezing rain and affected instruments, and there was a lot of freezing. And so, rainfall in the wintertime didn't, happen every single winter, or didn't happen a lot every single winter, but definitely there's some years that stand out.
So do you think that affects your statistics throughout the season, throughout the year?
So in that box and whisker plot, that's not necessary. So I'm not trying to wait to say oh yeah, all Januaries have these melt layers that are really close to the surface, and so I don't think that that's showing that. So I don't think the statistics are skewed because we're really just trying to assess when does this happen, or where does this happen in the atmosphere, and is it concerning? Is it in this point zone? And so I think it could be a fun thing to look at, what are the conditions going on for those years that we did have rainfall in the wintertime, so cold season rainfall. And actually, Marion Maitling has a paper looking at atmospheric rivers, and when there's an atmospheric river event reaching Marquette, then that's higher likelihood of rainfall, because these are warmer, high moisture events. So some of those ARs lead to the winter rainfall. So that's could be connected to that as well.
In a short follow-up, you showed that the wet bulb altitude from the reanalysis actually did a very good job of capturing, but I think you said that you kind of had to make it a 2 degrees C because the instrument wasn't detecting it wasn't detecting the precipitation as soon as it occurred.
Right, so at 0 degrees wet bulb temperature, that's when melting starts, or that's defined as, at that wet bulb temperature melting begins. And the radar is detecting essentially, so first we have the bright band and the reflectivity when the particle becomes reflective because it has liquid coating, but then it starts to accelerate and fall faster. And so that's really what the Doppler velocity is detecting once we're falling faster, or once we're kind of in that transition of more rainfall. And so that's why it's not quite matched up at 0. And I think if we were to look at reflectivity, that bright band happens a little bit above the Doppler velocity signature. And so that's, what variable I used does make a difference of what at that matchup.
Go ahead.
Yeah, that was very enjoyable. I didn't realise CloudSat was referred to as a fat cat. Never been done that way before, but just the comment on the blowing snow. There's been a lot of work done on looking at blowing snow using CLIPSO LiDAR. So if you were already go down that path and look at really shallow stuff, you might want to also look at the LiDAR.
Right.
LiDAR observations. Of course, you have to go back in time because CLIPSO's now dead.
Okay.
And clouds is about to be turned off in September, so you won't use retrospect. I think the LiDAR is worth looking at too for snow. Like Mark, I don't know whether Mark's looked at it or not.
No, I haven't.
Done any of the blowing snow stuff with LiDAR. But there's been a community out there really doing a lot of blowing snow stuff with LiDAR, so that would be a place to look if you wanted to go down that path.
Right. Sounds like a fun place to start Google Scholar, the LiDAR and
A lot of this stuff's probably up to the thing. The LiDAR can get through that stuff.
Thank you.
Yep, there's another question at the end.
So I just want to say, first off, amazing presentation. Second, JP, I will be lucky to have you. And third, my question is, so you use reanalysis from ERA and NERA2 to kind of provide validation or closure. Is that a customary practice? Because obviously reanalysis, they have issues with this kind of stuff too. And what are those potential issues with the reanalysis if you know?
Right, so for a number of studies looking at the melt level or freezing level or rain snow level, there's a lot of different names, bright band, there's a few papers that do compare to reanalyses, particularly in places where there's no soundings. And so Marquette is one of those sites. We don't have soundings. The closest ones I think is Green Bay, maybe Duluth as well. And so we don't have soundings at the site. And so we essentially are using the radar to then assess the reanalysis. And there's a few papers that look at that, looking at the freezing level. And I think there's some in South America, particularly in connection to glacier mass balance. And so there's a few papers looking at that. But there are those challenges with reanalysis. So we have the spatial resolution, ERA5, and MERA2 have different resolutions. And so when I look at reanalysis, I'm looking at like the closest point to our sites, and then for North Slope, I'm interested in as close as possible, but then also on land. And so there's a little bit of spatial differences when using these products. And then I know that, I think it's MERA2, that there's some issues over the Great Lakes. And so how lakes are treated and also land is treated differently. I think it's MERA2. We could discuss more about that.
Great. We have time for another question if there is one. If not, I'll just wait for a second. Yeah, go ahead, Brad.
I just have to follow up on Graham's point. So Norm, has, I think in North Dakota, you were looking at blowing snow. And we do have the CL61 that's got, polarized channels, and that would be, I don't know that there was a PIP or anything out there, but that might be.
There is.
There is,
Yeah.
yeah, okay.
And we had a year of it at Marquette.
Okay, good.
So we can look at blowing snow.
Yeah.
Right, if I'll make a follow-up to this too then, I was working with Helen Schepfer in France, and we actually do have a prototype combined CloudSat Calypso snowfall product that is also under development, so, and this work motivates it perfectly. I think Julia just sort of set the stage for us to put that product out as well, so. Okay, with that then, thank you for an excellent presentation, Julia. Should invite somebody to take some of the sweets that were set out here. I didn't even realize they were there.
Early career first.
Early career first.
Yeah, early career first, then others. And within about 5 minutes or so, after everybody sort of vacated the room, I'll ask the committee to reconvene here.